Round-robin scheduling is just one kind of scheduling. Others are possible. You can imagine, for instance, if you have a couple of programs running, right? One is trying to compute pi to x number of decimal, k number of decimal places, and one is you're actually trying to do your homework in some way. So do you want to give equal time to your homework process and your sort of background calculating pi process? I don't think so. Maybe it's not calculating pi. Maybe it's mining Bitcoin. Who knows? But you're in a rush for one of them, and the other one's kind of best effort, is how you could think of it. So you might also have priority scheduling. So in priority scheduling, every process has a priority, and you favor higher priorities. How do you favor higher priorities? Well, one way you can do it is go ahead and run all processes that are at a higher priority before you run any processes at a lower priority. So basically, you would go through the process table and find the process with highest priority. If there are multiple such processes with high priority, you can go ahead and do a round robin between them. But only when one of them is non-runnable do you bother trying one at a lower priority. The problem with that is starvation. So potential problem is starvation. That you're going to be ignoring these low priority processes completely. Maybe that's what you want, maybe not. One solution to that is what's called a lottery scheduling. In lottery scheduling, you still have a priority, okay? But what you do is take a lottery of everyone's priorities. So you take all the priorities and you sum them together. That's the total number of tickets there are in this lottery. And the number of tickets every process gets is based on its priority. So for instance, if you have procedure 1 with priority 15 and proc 2 with priority 2 and proc 3 with priority 3, then we have a total of 20 tickets. And basically, procedure 1 is going to have a 3/4 chance of running at any time. Procedure 2, 2/20, and procedure 3, 3/20. So what that's really going to say is, over time, average, procedure 1 is going to get 3/4 of the CPU time, procedure 2, 10%, and procedure 3, 15%. And so at scheduling time, all you really have to do is know what this total is, flip a coin, flip a random number generator, let's see, between 1 and 20, and then choose appropriately from here. So the lottery scheduling can solve all of these issues with potential starvation. Another potential problem might be if you have two processes. Let's say one is connected via a pipe to another. So you've got a reader that's reading from a writer. But the writer is extremely low priority and the reader's high priority. The reader can still just be stuck because the writer is at this low priority. So one thing that can happen is if you've got a high priority process waiting on a low priority process, the low priority process could inherit the priority of the high priority process. These are just some of the scheduling. Other scheduling you could do, for instance, if you've got a process that is I/O bound, so it does a little bit of CPU and then it issues an I/O request and is waiting for I/O. That might be something you want to run more often than something that is more CPU bound. So the idea is that if you're running something that uses little CPU and then it goes down and waits, and then when it comes in, it does a little bit of CPU, and then here issues a system call that does I/O, and again it has to wait, that your expectation is that if you were to run this process, if it has behavior similar to how it's acted in the past, that it's not going to use much CPU time, that it's going to issue a system call again for I/O, and that's going to cause it to be waiting. And so you might prefer to schedule a process like this than another process that goes ahead and, so here's a system call, and this is the timer. So the timer causes it to not run. And then it runs its entire quantum. So your expectation is if you send this guy into the field, that this guy is going to use its entire quantum. So you might want to take that into account. You could take that into account as you're doing your scheduling and prefer I/O bound to CPU bound. That's what this is normally called, I/O bound, that it tends to be doing more I/O than CPU, and this is more CPU bound. May occasionally be making I/O calls, but normally it's using up its entire quantum. So there are lots of different kinds of scheduling. These are some examples.